right, so today, continuing with Unit 6 and thermodynamics, we're going to talk about the concept of enthalpy, what it is, how we can find it, and how we can use it to find the energy that is released in a reaction. So let's go ahead and jump into our PowerPoint. Okay, so all about enthalpy today. So before we can really start talking about enthalpy, we really need to define what it is. So we've been talking about all of the different energy changes that accompany a reaction. And we're going to back up just a little bit, and we're going to talk about energy in general. So any system has what we consider to be an internal energy. So that's the sum of all of the kinetic energy and the potential energy of a system. And we call that energy E. That's the internal energy. By definition, the change in internal energy is the final energy of the system minus the initial energy of the system. And remember, that's because energy is a state function. So it doesn't matter how it gets from initial to final energy. The change is just going to be final minus initial. The pathway doesn't matter. So where does that change in internal energy go? So we have these two terms. We've been talking about Q through this unit. Q is heat. W is work. So Q is the heat that is flowing in or out of the system. It's negative if the energy is leaving and going into the surroundings. It's positive if energy is coming in from the surroundings. W is work, and that's work that's either done on the system or work that is being done by the system. Again, remember our perspective is always from the system. So it's negative if work is done by the system on the surroundings, and it's positive if work is done on the system by the surroundings. Now, when it comes to work in the world of chemistry, generally speaking, the way that work is done is through expansion. So for chemistry purposes, we're going to define work as negative of pressure times the change in volume. So that means that if our chemical change is causing an expansion of our system, we're going to have a positive change in volume, and that's going to result in a negative W, which means the E of the system is going to decrease. Now remember that negative work means that the system is doing work on the surroundings. And that makes sense when it's expanding. So if we go back to our example of a car and the way that an internal combustion engine works, when the expansion from the explosion of the gas and oxygen happens, that pushes up against a piston, it does work. It pushes the piston up, that turns a crankshaft, and eventually that makes our car go forward. On the other hand, when work is done to the system or on the system, that would be a compression. So we have a negative change in volume, a decrease in volume. That's going to result in work being done on the system. The energy of the system is going to increase because work has been done on the system by the surroundings. So in an open container, the only work done is by a gas pushing on the surroundings or the surroundings pushing on the gas. For our purposes, well, let's back up. Most of the processes that we talk about are being done at constant pressure. So the only work done is pressure volume work. That means that all of the heat is accounted for by measuring the enthalpy of the system, because enthalpy is technically the internal energy plus the product of pressure and volume. So if we take this same equation, we know that enthalpy, H, is equal to the internal energy plus pressure times volume. If the system changes at constant pressure, then the change in enthalpy is the change in energy plus pressure times the change in volume. which we can write this way. Delta H equals delta E plus P delta V. Since the change in internal energy is heat plus work, and work is negative pressure times the change in volume, when we substitute these in, we get that delta H equals Q. So if we're working at constant pressure, which we almost always are in the AP chemistry world, the change in enthalpy is the heat gained or lost. So we will, from here on out, use the terms enthalpy and heat interchangeably, okay? But there's one key difference that you need to stay aware of. We can use Q to determine delta H. Q, the way we calculate it, Q equals M times specific heat times the change in temperature. That's the heat that's gained or lost in a reaction as it's performed. But delta H is usually for a reaction as it's written. So delta H assumes that we have 1 mole or 2 moles or whatever the coefficients are of reactants. Q is an experimentally determined value. And so it's as the reaction is performed. So this means in order to find delta H, if we're given experimental data, we're going to divide Q by the number of moles in the reaction as it was performed. And that's going to give us a delta H in units of kilojoules or joules per mole. So let's practice that. So we have this chemical equation. We have magnesium plus hydrochloric acid yields magnesium chloride and hydrogen gas. So when we have 12.15 grams of magnesium added to 500 milliliters of 4 molar hydrochloric acid, it produces 95 kilojoules of heat, and it asks us to find the enthalpy of the reaction. So the first thing we're going to do is we're going to remember that delta H is equal to Q divided by the number of moles. Now, we have 2 different amounts of moles. We have a mass of magnesium and we have a molarity and a volume of hydrochloric acid. So we're going to take a look and we're going to see that we have 1/2 of a mole of magnesium and we have 2 moles of hydrochloric acid. That means that the hydrochloric acid is in excess. So we're going to divide by the moles of magnesium because that's all that reacts is the 1/2 mole of magnesium would react with 1 mole of hydrochloric acid. So our delta H of the reaction is going to be that 95 kilojoules, remember, and because this is being produced, we're going to put a negative sign on it, divide by the number of moles, and we know that this reaction is going to have 190 kilojoules per mole released. Always make sure that you write this, and you can see that I have the mistake here, 190 kilojoules per mole of reaction. So make sure that you're using the reactant that there is only 1 mole of in your balanced chemical equation. We wouldn't want to divide this by the moles of hydrochloric acid. We want to divide it by the one that has a coefficient of 1. Okay, so if we're given experimental data, we just need to make sure that we convert Q to delta H by dividing by the number of moles. Now, if we're working from more abstract data, from more theoretical data, one of the things that we can work with is something called bond enthalpy or bond energy, and we can use bond energy to estimate the heat of reaction. So we know that all reactions are breaking and forming of bonds, and that breaking bonds is always endothermic and forming bonds is always exothermic. The amount of energy it requires to break a bond is what we call bond energy or bond enthalpy. So for example, this chlorine to chlorine bond has an enthalpy of 242 kilojoules per mole. That means in order to break that bond, you would have to put in 242 kilojoules per mole of chlorine. So we can use this information. There are tables that give us average bond enthalpies. And so we can use this information to determine the enthalpy of a reaction by determining what bonds are broken and knowing that much energy has to be put in, and what bonds are formed and knowing that that amount of energy is going to be produced. So we can compare enthalpy of bonds broken to the enthalpy of the bonds formed, and that's going to allow us to calculate the enthalpy of the reaction. So enthalpy of reaction is going to equal the sum of the bond enthalpies of the bonds that are broken minus the sum of the bond enthalpies of the bonds formed. Remember, this is the amount of energy we have to put in. This is the amount of energy that we get out. So by having the negative sign here, the minus here, that means that we're going to have amount we put in minus amount we get out. So if this number is negative, that makes sense. That's our delta H of reaction is going to be negative. So we are going to get out more energy than we put in, and that would be an exothermic reaction. Conversely, if we put in more than we got out, it would be an endothermic reaction. So we have this formula that delta H is equal to the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. Energy required minus energy released. Remember, breaking bonds is always endothermic. It always requires energy. Forming bonds always releases energy, is always exothermic. So we'll look at another example, or an example, I guess. So we have methane reacting with chlorine gas to form methyl chloride and hydrogen chloride gas. So in this example, in order for this to happen, one carbon to hydrogen bond has to break, the chlorine to chlorine bond has to break, and then a carbon to chlorine bond is formed and a hydrogen to chlorine bond is formed. So we're going to look at our table of average bond enthalpies here. Remember, one carbon to hydrogen bond and one chlorine chlorine bond are broken, one carbon to chlorine and one hydrogen chlorine bond are formed. So we would look at this table of average bond enthalpies, and we know we're going to break one carbon to hydrogen, and we're going to break one chlorine to chlorine. So we would have 413 plus 242 minus, now we're going to form a carbon to chlorine bond, which is 328. And we're going to form a hydrogen to chlorine bond, which is 431. So our delta H is going to equal bonds broken minus the sum of the bonds formed. So we have the 413 plus 242 minus the sum of 328 plus 431. And we get 655 minus 759, and we get negative 104 kilojoules per mole of reaction. So remember, broken minus formed. Let's do one more practice example here. This table is table 8.4 in your book. I have it on the slides as well. Says that this is asking us to estimate the delta H for this reaction. We have this N2H4 compound forming nitrogen gas and hydrogen gas. So let's switch our screens here for just a second. Okay. So we had nitrogen, nitrogen, hydrogen, 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 and this decomposed into diatomic nitrogen and 2 diatomic hydrogen. So we're breaking a nitrogen to nitrogen bond. and we're breaking all of these nitrogen to hydrogen bonds. So we're breaking 4 nitrogen to hydrogen bonds. And when we look at our table, where we see that the bond enthalpy of the nitrogen to nitrogen bond, single bond, is 163 kilojoules. And the enthalpy of the nitrogen to hydrogen bond is 391 kilojoules. And then we see that what's formed is a nitrogen to nitrogen triple bond, and we form 2 hydrogen to hydrogen bonds. And again, we look at the table and we see that the enthalpy of this bond is 941 kilojoules. And we see that the enthalpy of this bond, the hydrogen to hydrogen bond, is 436 kilojoules. And so delta H is going to be the sum of the enthalpies of the bonds that are broken minus the sum of the enthalpies of the bonds that are formed. So we're going to have 163 kilojoules plus 4 times 391 kilojoules, because we have 4 of those bonds that are being broken, minus 941 plus 2 times 436. And so, quickly do some math here. We have 1,727 kilojoules minus 1,813 kilojoules. And we get negative 86 kilojoules. And so we would say that the delta H for this reaction is equal to negative 86 kilojoules. So this is an endothermic reaction. Okay. Back to the PowerPoint. There we go. Okay. All right. There are a few more practice problems in the PowerPoint if you want to take a swing at those. But we're going to move on and talk about enthalpy of formation. So first, we need to define the idea of enthalpy of formation. So enthalpy of formation is defined as the enthalpy change for the reaction in which 1 mole of a compound is made from its constituent elements in their elemental forms. So it's the energy required to form 1 mole of a compound from its constituent elements. Standard enthalpies of formation are measured under standard conditions, which is 25 degrees Celsius and 1 atmosphere of pressure. So let's go back to this idea of enthalpy of reaction, because we talked at the beginning about the idea that it doesn't matter how we get from the start to the finish, the change in energy is going to be the energy of the end minus the energy of the beginning. And so we can apply that idea to the enthalpy of reaction. And we can say that, well, the enthalpy is a measurement of internal energy. So the enthalpy of the products minus the enthalpy of the reactants would be the change in enthalpy of the reaction. And so products minus reactants. Now this is a change from broken minus formed, and it's actually going to kind of wind up being opposite in terms of what winds up where. So please be careful. Delta H of reaction is equal to the enthalpy of the products minus the enthalpy of reactants. Now, you want to make sure that you multiply by the stoichiometric coefficients. So if there is a coefficient in the balanced chemical equation, we want to make sure we multiply by that. So if we look at this reaction, the reaction between propane and oxygen, this is a combustion reaction. We're going to look at tables of standard enthalpies of formation. And there are lots of these tables. There are tables in your textbook. These are values that would be given to you in the AP exam. So enthalpy of formation, so we can see, remember, products minus reactants. We have 3 moles of carbon dioxide as a gas. Now, it's important to pay attention when you're looking at these standard enthalpies of formation to the state of matter, because the enthalpy of formation of gaseous carbon dioxide is different from the enthalpy of formation of liquid carbon dioxide. Enthalpy of formation of gaseous carbon dioxide is negative 393.5 kilojoules. We're going to multiply that by 3 because we have 3 moles of carbon dioxide. The enthalpy of formation of liquid water is negative 285.8 kilojoules. We're going to multiply that by 4 because there's a stoichiometric coefficient of 4. And then we're going to subtract the enthalpy of the reactants. There's only 1 mole of propane. So there's the enthalpy of formation of propane, 103.85 kilojoules. And then because oxygen is its elemental form, the enthalpy of formation of anything in its elemental form is just 0. And so we have 5 times 0. So we do the math, multiply by the coefficients, and we wind up with negative 2,323.7 kilojoules minus negative 103.85 kilojoules. And we have the enthalpy of this reaction is negative 2,219.9 kilojoules. So this reaction gives off a lot of energy, which we would expect. This is a combustion reaction. Okay, we will practice lots of these in class. Remember, products minus reactants. This equation is on your equations and constants sheet. So just a couple of reminders about enthalpy. Enthalpy is an extensive property. It depends on how much of something there is. And so this is why we'll often see it expressed in kilojoules or joules per mole, so that takes it to a consistent and constant value for a reaction. Delta H for a reaction in the forward direction is equal in size but opposite in sign to the delta H of the reverse reaction. So if the forward reaction gives off energy, the reverse reaction takes energy, but it is the same amount of energy. Just the sign is different. And then the delta H for a reaction does depend on the state of the products and the state of the reactants. So pay attention when you look up enthalpies of formation. As always, if you guys have any questions, let me know.